Okay, welcome to the ninth lecture on satellite attitude dynamics and control. So, today we will discuss about the rotation about a fixed vector. Already we have been discussing about this. So, as you can recall that we have written the rotation matrix C as I cos phi plus 1 minus cos phi A tilde transpose minus sin phi A tilde cross. Okay. And then we saw that if we are looking for two consecutive rotation, composite of two consecutive rotations. So, where the first rotation is given by A 1 tilde phi 1 and the second rotation by A 2 tilde phi 2. Okay. So, composite of these two rotations, the equivalent of these two can be given by. So, this implies the whole rotation should be about one single axis, which is given by A tilde 3, where A tilde 3 is again the unit vector. All this A 1, A 2 these are the unit vector, and this is by rotation by phi 3 angle. So, these two rotations phi 1 and phi 2 about A 1 and A 2 respectively are combined together. They combine together are equivalent to A tilde 3 rotation about this vector by angle phi 3, and this we have obtained some expression for this. So, we will get back to that, but before this I told you that we will be discussing about indeed that this rotation matrix is a rotation about the vector A tilde by phi, that we have to check geometrically. So, that we have not still done. So, today we are going to do that. So, say this is our E 1, E 2, E 3 cap, this is the basis vector, and this is the vector A tilde. Okay. So, A tilde is a unit vector, remember. So, magnitude I am showing it in general like this, but magnitude may it has to be taken of a unit magnitude, but direction will be governed by whatever the say depending on what kind of rotation you have given. So, either we go from C to A and phi, or either from phi to C. So, here our objective is to given two rotations phi 1 and phi 2 about A 1 and A 2, and what will be the equivalent of that. So, this we have already done, okay, this part we have derived, and I will look back again into this. Today, I am going to verify this, that this expression is indeed an equation for rotation about a fixed vector A tilde. So, let us say this vector A tilde is here, okay, and rotation about this vector is given by so, this is your r vector, which is being rotated about this A tilde vector. So, we consider that this is along this direction. A tilde vector may be of unit magnitude. So, obviously, A tilde is not of this magnitude, but we are just showing it like this, that A tilde is along this direction. Okay. Now, we break this is my vector. So, I can break it into two portions, one along this direction and one along this direction, means one along the A vector and another perpendicular to the A vector. So, we can write here r equal to, okay, this will indicate by r normal, and this part we will indicate by r parallel. So, r will be equal to r parallel plus r normal. Now, this matrix, this is a rotation matrix. So, this is basically it shows the rotation of the frame by phi angle about the eigen axis. So, here in this case A tilde, this is indicating the eigen axis, A tilde is the unit vector. So, this happens to our eigen vector eigen axis about which this frame is being rotated. Now, instead of considering this frame, that this frame is being rotated, consider that just opposite of this, that this vector, there is a vector r which is being rotated from this place to this place by minus phi. So, if the frame is rotated, already we have seen that if we have one vector like this and we rotate the frame by theta. So, that is equivalent to rotation of the vector in the opposite direction by minus theta, keeping the frame fixed. So, the same principle is applied here. So, here after breaking these two, now we write it in a proper way. So, let us make a circle here. So, this is the component where which is being shown as R n. So, this is our R n vector. Okay. Now, the component of vector r along a direction. So, r tilde dot a tilde, this is the component of the r vector along the a direction, where this is indicated by r p. So, this is your r p tilde, and because it is along the a direction. So, we have to multiply it by vector a. Okay. So, now r prime, if we rotate this, say if we rotate it from here to here by minus phi, this angle is minus phi. So, we are rotating in the clockwise direction. So, frame rotates in the anti-clockwise direction about this vector by phi. So, that is equivalent to rotation of this vector in the opposite direction by angle minus phi. So, here we can indicate this, this is the minus phi angle. So, I will just write the magnitude here. Okay. So, it has rotated from this place to this place. So, this is your r n vector and this is the rotated r n vector. Okay. So, this is equivalent to that this r vector is there and this vector r you rotate from this place to this place. So, it comes from here to here. Now, this is the vector r. So, this is your r prime. Okay. So, r prime is here. So, it has rotated from this place to this place by angle minus phi, that is in the clockwise direction about the a tilde vector. Now, few things we can observe, that a vector is along this direction, r vector is along this direction. Okay. So, now a cross r, in which direction it is going to lie? A is along this direction and r is along this direction. So, if you put this r from this point, so you will see that it will be perpendicular to a cross r will be perpendicular to both a and r. So, r is in this plane here, r is forming by this plane, this particular line, this green line and this is the orange line. So, it is a perpendicular to this. So, means it will be perpendicular to this vector r n, and we will show this, this is your a cross r, a tilde or either a cross r, where a is a unit vector. Now, why it is on this circle? There is a reason for this. If you look into the magnitude of this a cross r vector, so this will be a magnitude times r magnitude times sin theta, and this quantity is 1. So, therefore, this is r sin theta. And what is r sin theta? If you look into this, so this angle from here to here, this angle is your theta. Okay. From green line to the orange line, this angle is theta. So, r sin theta is nothing but your projection of this r vector along this direction, that is the magnitude of r p vector. This is the magnitude of the R p vector, sorry, this the R n one. Okay. So, this is projection here along this direction, this is R n. So, this angle is theta and therefore, this is here this quantity. So, A cross R, its magnitude remains equal to the magnitude of R n, therefore, it lies on this circle. Now, again if we take A cross R, means we write it like this. So, you will see that A vector is along the normal direction, it is a coming out like this, okay, it is a coming out here out of the page, okay, and A vector is along this direction. So, A cross R taking the right hand rule. Okay. So, it goes here. Now, this is perpendicular 90 degree, this angle is 90 degree, we are so 90 degree angle we will show like this. So, therefore, perpendicular to this will be again here in this place, which this vector will indicate by A cross R. Again the magnitude of this vector A cross R, you will see that this is A cross times A cross R magnitude. So, this quantity is 1 and already we have seen that this quantity is r sin theta. So, this gets reduced to r sin theta, means this is also equal to the magnitude of R n. So, this is also the magnitude of R n. So, it lies here in this direction. So, opposite of this vector here in along this direction, this is minus A cross R, and similarly opposite of this from here to here, this will lie along this direction, and that we will write as minus, with minus sign we have to write minus A cross R. Okay. So, this is 90 degree, this is 90 degree. So, just opposite of this. So, it will lie somewhere along this line. Okay. Now, this is the projection of the vector. So, if this is r prime, and so this is r prime normal, this is r prime normal, okay. Means r prime again can be broken along two directions, one along the A direction and one perpendicular to this, which will we are showing here as a circle. So, it is a this vector being shown here. So, r prime, this we can write as r prime parallel plus r prime normal. So, here this is nothing but your r prime normal. Now, this vector it can be so, this vector of minus A cross R we have already shown here, and this is our r prime n. So, now the new vector consists of this one. So, if we can define this r prime n, so our job will be done. So, for defining r prime n, we see that this is component of this vector along this direction and then component of this vector along this direction. So, we can write here r n prime this equal to minus A cross R along this direction, which is cos 90 minus phi, and component of the vector along this direction, and we have to take the component here, this vector in the opposite direction and component along this direction. So, this is minus A cross R times cos phi. Okay. So, this is your r prime n, this is a normal component, and if we combine with this r p prime, okay, which is the parallel along this direction. So, I will ultimately get the final result. So, your r p prime this is nothing but your r p. So, we just need to add this. So, final addition So, how our vector r prime will look like? This is r prime p plus r prime n, and this is equal to r p plus r prime n, and r p is the component of vector r along the a direction. So, this already we have written, either you write in vector notation or matrix notation, it does not matter. So, here we are using the vector notation. So, this is the this part, and this part already we have written. So, we just copy that. So, this is a cross r cos 90 minus phi and minus a cross r sin phi. So, this is our rotated vector. Now, we have to get this into the matrix format to see that everything is correct. Okay. So, one more step we will simplify this as this is sin phi. So, this is a cross r sin phi, and this we need to work out. Okay. Yes, sorry, this part is here cos phi. We have written cos phi, so by mistake here this is cos phi. So, this is our cos phi. Now, we need to rearrange it to get the solution what we are looking for. Okay. So, first of all we will explore this, what this quantity is, a cross r. Okay. We need to expand and look into this exactly what it is indicating. So, if we expand it, so this turns out to be a dot r a, okay, a dot r a minus a dot a r. Now, a dot r, this quantity, what this is, we have to look into. A dot a, obviously we know this quantity is equal to 1, because the vector a is having magnitude 1. So, writing this here, now a dot r, this is the angle between, this is the projection. So, here what is the angle between these two vectors, between the a and the r vector, that we have to decide. So, what we do, that we write in a way where ultimately it comes in this format what we have been looking for, C equal to I cos phi plus 1 minus cos phi A times A transpose minus sin phi times A cross. This is what we are looking for. So, we will try to reduce this vector into this form. So, ultimately this what is happening, that there is a matrix which is operating on this vector r, okay, and that rotates and gives it a, changes it to the vector r prime. So, ultimately our objective is to reduce it to this format. So, what this quantity is, just 1. So, this is a times a dot r minus r. So, r prime is our we will write this as this part we are writing, just taking sign ahead of this. So, this is sin A cross and r. So, what our strategy will be to take out this r out of the bracket. Okay. So, if we are able to do this, my problem will be solved. So, copying from this place A times A dot r minus this quantity, okay. It will come here in this place. So, A dot r and plus this minus r times this cos phi. Now, what we see that here something is common between these two terms. Okay. So, we write this as A times A we take, and this is a scalar, this is the dot product. So, this is a scalar quantity. So, that becomes 1 minus A times A dot r times cos phi. So, this is we take it outside the bracket, this is A dot r times 1 minus cos phi, and here we are just left with plus r cos phi minus sin phi A cross r. This quantity, as we will show, that if we write this as we will do little arrangement, we will put this term here in this place. So, this is r cos phi plus this quantity thereafter 1 minus cos phi A times A dot r, and thereafter this quantity sin phi A cross r. So, going on the next page. So, our r prime, that becomes r cos phi then 1 minus cos phi. So, what we are going to do now, that write it in a matrix, convert it to a matrix format. Okay. So, for doing this, so what our strategy will be, just take it r outside. Let us write the r out of the bracket. So, we write r here in this place. Okay. Now, look here in this place, this is r cos phi, this is a vector, okay. And if I take it outside the bracket as here in this place, so I must put here cos phi times identity matrix. So, this is a vector which operated, once it operates on I, okay. Here this is a I matrix, and you have here r 1, r 2, r 3. So, when any vector is multiplied by the identity matrix, it remains as the it remains intact, and therefore, either we write it here in this format or either in the matrix notation, that is like in this way, it does not matter. So, we have taken it outside. The next term, once we go for this term, so this is 1 minus cos phi and A dot r. Okay. So, here 1 minus cos phi A times A dot r. So, here we will write this as dot. So, this is here dot written, and this quantity, as we will show, this is equal to A tilde transpose. r we have taken outside. So, this is operating on this r, and thereafter this particular term a cross r. So, r is taken outside. So, this remains minus sin phi a cross. So, we next get minus sin phi a cross. So, this is a cross, and finally, obviously, we will instead of writing this a and this arrow, rather than writing, we write as a tilde, which is indicating the vector here in this format. Okay. So, we have this cos phi I plus 1 minus cos phi. This quantity will show as it is equal to a tilde transpose minus sin phi, and this is nothing but your a tilde cross, which is a skew symmetric matrix. And this is operating on here r. So, we can indicate this as the r tilde, and this is r tilde prime. So, this vector, it operates on this vector, and it converts this to r prime. Means what this is indicating? This is indicating the rotation of vector r by minus phi, rotation of vector r by minus phi. Okay. And this is equivalent to rotation of the frame, rotation of the frame by phi, which is anti-clockwise, and this is clockwise. So, this indicates that r tilde prime, this can be written as c times r tilde, and where c equal to cos phi plus 1 minus cos phi times I, 1 minus cos phi a tilde transpose minus sin phi a tilde cross. So, this is what we have been looking for. Only thing remaining is that we need to look into this a times a dot, this is equivalent to, this is an identity basically. So, this is a tilde times a tilde trans. So, let us look into this here this way. If I put it this as the r, okay. So, this is nothing but a tilde, and this is a scalar. Okay. So, we can write this as a tilde transpose times r tilde. Okay. Now, if we combine this together, so this becomes a tilde times a tilde transpose, and this is. So, ultimately this is a vector, okay. And here this itself is a scalar. Okay. But if we write it in a way where this part we have broken as a tilde transpose times r tilde, which is the inner product, that is a dot product, and then separated out this. Okay. So, once we separate out, it gets into this format. So, this implies that a times a dot, this equal to a tilde times a tilde transpose. So, this is what has been used in the previous one. So, this proves that indeed the C matrix is a rotation matrix which rotates any vector r about the fixed vector a, which is in this case the eigen axis. Now, from here we go into the Euler's theorem, which we have been working with. So, what we have this is basically part of the Euler's, this is Euler's theorem itself, but what we are going to do, we are going into the Euler's parameter now. So, we will convert this so that this indicates the Euler parameter rather than the a vector, which is a vector, this is 3 dimensional one, okay, a1, a2, a3. While we write in the Euler parameter terms, so Euler parameter it is a 4 variable system, okay, in which as I have told you that if I indicate this Euler parameter by E tilde. So, E tilde transpose E tilde plus eta squares, this will be 1. Okay. So, these are the Euler parameters, epsilon tilde, this equal to epsilon 1, epsilon 2, epsilon 3. These are the 3 variables involved, and this is or the parameter, and this is one parameter. So, we are going to look into this. So, this is showing that this is a 4 parameter system, but actually only 3 independent coordinates, okay, because its a dependence is shown by this equation, where epsilon is related to eta is related to this quantity. So, eta can be expressed in terms of epsilon 1, epsilon 2, epsilon 3, but it has got its certain advantage which we are going to discuss. So, thank you for listening. We will continue in the next lecture. So, thank you again.